There we go.
Yeah. No, it wasn't. Yeah.
Okay.
Yeah. So, yeah, we figured it out. So thank you so much, everybody, for taking out time. I would like to start my talk by thanking Corey for giving me an opportunity to visit RIT. I've been wanting for a long time, and then there was this COVID. So I'm very thankful that I got to see such a beautiful campus and meet everybody. So very thankful for that. And then thank you to all the faculty who took out time to talk with me and spend some more time. So that was great. So with that, and also I got to see such a great campus with the Santosh always used to talk about clean room, but unless you see, you don't believe, right? So seeing is believing. So definitely you guys have a great clean room microfabrication facility. So awesome. So with that, I would like to start my talk. My research is focused on emerging memory devices. So today my talk is going to be in that area. So emerging memory devices and their application, particularly memory devices, are becoming extremely important for machine learning and brain-inspired computing, together the neuromorphic computing. So I'm going to talk about that today. So a little bit about my research program, what we have been doing. This pyramid probably try to fit everything. So electronic materials is where you try to develop the material. We don't do too much of material development, but we take the materials that is already out there and is proven and make devices out of it. And that is where this clean room is very useful. And you guys already have a great starting point. So advanced CMOS and beyond CMOS devices. In terms of advanced CMOS, we try to make novel logic and memory devices that can fit into the Moore's law map. And beyond CMOS is something that is not exactly, the operation principle is not derived from the CMOS technology, but it could be a different operation principle. The type of devices we investigate in this area is resistive random access memory devices, also ferroelectric field effect transistor. So we can do device design, simulations, fabrication, testing, and TCAD modeling. So this is core of our research. We investigate FEFET, RRAM, advanced CMOS. We have started to do some research on 2D based CMOS. And then I was talking to Kai also, and he spoke about thin film transistor could have some future in the areas of back end of the line. We have exported this device not for any of these applications, but for some biosensors application. But again, integrable on CMOS. And then we do some research on circuits and architectures, but for the purpose of showing the community what our devices could be useful for. And I was talking to Mike and Cody yesterday that, we have to show some where our ingredients are useful in a recipe to attract your attention. So that's the region we do some circuits and architecture. And finally, over it is neuromorphic in-memory computing. So we take these devices, create models, and try to use some higher level languages like Python or C++ to show how it is useful. The areas our research is targeting is novel computing paradigms, definitely AI ML, cognitive communication that I'm very interested in, trying to find some collaborators, sensors and IoT, high performance computing, mostly with the advanced CMOS and autonomous system. My research in this area has been funded by National Science Foundation, very thankful to them. And then Air Force Research Lab, and we have the center, IUCRC, for hardware trust and security to that. And then some funding from Intel. And in Ohio, we have a very unique funding opportunity for students, particularly the domestic students, called SHOCHI, where if you show that somebody from Air Force Research Lab, Wright Patterson, is interested in working with you, and you have an American citizen student who wants to do PhD, then 3 of you can form a team and state gives you money to do that kind of a research. So this scholarship is given to the students. So I was recipient. A few of my students were recipient. And then this NIOSH, I don't know how many of you know, but it is a part of CDC, and it stands for National Institute of Occupational Health and Safety. So these days they are very interested in making use of AI for workplace safety reasons. Like the way workers lift something could damage their back, so they use a lot of wearable sensors and make use of AI to detect things. So this is how my research portfolio is right now. And so this is the outline of my research for today. I'm going to talk a little bit about data storage needs, particularly for the sake of students. you guys know that we need a lot of data to be stored, and embedded SOC requirement, and neuromorphic computing, how it fits in this whole domain. And then I'm going to talk about my research in the area of 2T resistive random access memory, two categories of it, mostly going to talk about filamentary RAM, and then dynamic state memory, where I'm very interested in seeing if this retention of this device decays over time, what kind of new architecture we can use it and leverage it for what kind of application. And then a new category of device, which is called gated RAM, which is a advancement over two terminal RAM devices. And finally, I'm going to talk about ferroelectric field effect transistor and how they can be used for some novel computing paradigms. So data, this is a chart that I took from here, but more or less all of us are convinced that, well, we need to store more data. So what are the memory technologies that can store more data? The non-volatile memory technology is mostly dominated by NAND, but a lot of people think that they are reaching their limits. Also, NAND has endurance issues. You cannot cycle it more than 10 to the power 3 or 10 to the power 4. And for on-chip memory application, they operate at pretty high voltage compared to logic devices. The right voltages are 15 volts or so, while logic is more towards 1 volt. So NAND, though it is very interesting technology, we need other memory technologies that are non-volatile in nature, which could be integrated with the CMOS. So that is what is the gist. Additionally, there are a lot of applications that are emerging where you don't need to particularly crowd to do computing. You can have edge devices where you need to do computing. Examples are, for example, implantable medical devices. So what kind of computing we can do on them? And wearable IoTs, we all know the wearable watches and all, how they are becoming more and more computationally active. Autonomous car is another big one. And then generally data analytics, where people use a lot of clustering techniques and stuff like that. So these are just some examples, but novel ways of doing AI on these edge devices are becoming extremely critical. But then, though AI and processors are there, they are limited by this memory bandwidth bottleneck, which is where people think that new memory devices will make a lot of impact. So this is a standard diagram I have taken from this Vivian Z's paper. You could see that these are your process engines, and this is your ALU. And she talks about how if you look at the normalized energy cost in terms of fetching data to this ALU from various of these memory hierarchy, how much it is going to cost. So if data comes from this register files, then it is 1x. If you get it from this process engine to ALU, it is about 2x. If you get from this global buffer, then it is 6x. And if you get it from off-chip DRAM, it could be about 200x more expensive in terms of energy. So that is why this has led to this whole area of getting memory closer to the processing and things like that. And then there is this roofline chart that shows here you have teraops per second, and then here it is operational intensity. Probably some of your students have read it in your computer architecture classes. And these are various types of machine learning algorithm kernels, and that is mapped to operation intensity. So most of these machine learning algorithms, their operational intensity lie in this slanted portion of this roofline chart, which means that they're limited by this memory bandwidth requirement. So this is a very nice paper, about 10, 11 pages. If you're interested, you can download and see. So all these limitations has inspired novel paradigms of computing, such as in-memory computing or process-in-memory or near-memory computing, or altogether coming up with the new memory technologies for computing. So my research is into emerging devices. So what are the emerging memory devices on the table, right? So there are tons of devices. Okay, so this one device is not like a winner. A lot of devices. So synoptic devices, you can see resistive RAM, phase change, electrochemical ECRAM, which actually was proposed by IBM. And then floating gate is adaptation of flash memory devices and capacitor on the gate. And then these are various other types of even photonic, magnetic, ferroelectric, all types of devices. And then we have this stochastic site type of devices, oscillator type of devices, and then computational kernels. Using these devices, you can make synaptic inferencing, synaptic training, stochastic synapses, various types of neurons and array-based where you can make matrix vector multiplication and stuff like that. So using these devices, you can integrate them in emerging kernels, which are derived from these devices. And then finally, you can make these into this emerging system. Together, they fall in this category of device technology co-optimization or system technology co-optimization and things like that. So in past, I have done a lot of research on resistive RAM. So this is the table which is comparing DRAM, NAND flash, phase change, FERAM, STT-RAM with resistive RAM. One of the major advantages of resistive RAM is it's very simple, very easy to integrate in CMOS backend of the line. So if you calculate the cost compared to any of these, it is pretty cheap. It is pretty scalable. You can make a 3D configuration by putting them on top of each other. Write erase time is relatively slower compared to DRAM, but still pretty fast compared to flash. And then retention at room temperature is more than 10 years. Durability, the best reported value is in this range, and write erase voltage less than 1 volt. Read voltage could be very small, and write energy, if you compare it to established technologies such as DRAM and flash, it is still pretty high, but compared to phase change and STT-RAM, it's comparable or even better. So this technology has caught a lot of attention, but it also has drawbacks. So I don't want to sell this idea that, well, this is the way to go. It has a lot of drawbacks. One of it is variability. Another is I'm going to talk about how the operation principle, and you will see that operation principle is not governed by a physics, it's governed by defect and stochastic nature, which a lot of people don't like, because that does not give you a path of scalability and principle of operation. So how is this device operating? So this is the very simplistic device. You make a metal insulator and metal capacitor. And transistor is just used as a way to control current through this device. So this is your metal, and in between is insulator. And then to control the interface between top and this insulator, which is switching insulator, you can also design an interfacial layer, which is pretty commonly done. So first step to, this is how device comes out of the fab. First step you have to do is electroform it. So you have to break down this dielectric, nice dielectric, by passing a current through it. So you switch this voltage, you pass a current, and apparently you will see at some point the current through this device increases, and that is when you know that you have broken down the dielectric. But this is a soft breakdown, and that's why you have to control this current to cause this soft breakdown. And then you end up forming this filament. Now, what is the material of this filament? So material, that is where there is a lot of literature. Exactly, nobody knows what material it is. But people think it's some agglomeration of defects, or could be some metal from the oxide that has reduced and formed the filament. And then you do the first reset. So first reset is to retract the filament. Now you can see that a gap has been created over here. How does that happen, right? So people think that some kind of redox reaction takes place that repairs the defect, so filament retracts. So this is your first reset. So this is your first one-time conditioning that you have to do. And after that, device is ready for multi-time programmable memory. And so to set the device, to put it into low resistance state, you apply a set voltage, you reform the filament. So this is your low resistance state LRS. And to reset the device, you just reoxidize it by applying a negative voltage. These voltages are of opposite polarity. And then you retract the filament, you create a gap. So you end up having a high resistance state. So now between set and reset, you can toggle the state, and you can make it multi-time programmable. And in our lab, we can easily go up to 10 to the power 8 cycles of endurance. So these are the devices. When Sematech was here, we got it from Sematech, hafnium oxide, and then we also made it in our lab. Hafnium oxide, zirconium, tungsten, and tinitride. These are very nice ALD hafnium oxide. You can see the device shows very repeatable IV characteristic just from the fab. And then you have to electroform the device, which is also an art. So students spend a lot of time. So if you're not careful in electroforming, you don't see any switching. So that is discouraging. But if you are very patient and nicely electroform the device by reducing the parasitics and all, then you see very nice switching curve for these devices because we are able to form the control filament. One thing I want you to notice is the switching voltages are less than 1 volt, which is what is very promising for these devices. So we could cycle these devices several times. This is a retention at room temperature. We could get 1 order of change in resistance between low resistance and high resistance state. You can see that set reset voltages are very promising. Set current and reset current is 100 microamps, which is not what we want. We need to reduce the current to about 100 nanometer, because remember, if current is too large, then this transistor that has to control the current needs to be larger in size. So scalability becomes a question. Okay, so now we did a lot of studies on different forming techniques and how it impacts the reliability and endurance. So clearly you can see if you do a good electroforming technique, the one-time conditioning, you get very high endurance for these devices. If you could not do a good electroforming, the device endurance is not as good. So endurance is a function of how you condition your device in the beginning. So now other good features of this device is that you can get multiple resistance states. And for those of you who are working with AI and stuff, you know that if from one device you can get multiple resistance states, that means you can store more number of bits in a single device. So that's how you can make memory more dense. So low resistance state, just by controlling the current through this device, we can get 3 states, distinct states. And high resistance state, by controlling various stop voltages, we can get 3 states. So from this particular device, we could get a total of 6 states from one device, which is nice. But then most of the people propose to integrate RAM in crossbar arrays. So if you put these devices in crossbar arrays, you can make them very dense. But you also need to integrate this diode. Otherwise, if you don't integrate this diode, then you could have a lot of sneak current. Because these are just arrays of resistor. So if this device is your high resistance and these all are low resistant, and if you want to read this device, then the current will sneak through these parallel paths, and read current is going to be very high and inaccurate. So you need to have this access diode, which is more of a problem than the resistive RAM device itself, because the access diode has to meet these criteria, which is pretty stringent. Your diode should turn on at less than 1 volt. On current and off current of diode should be this ratio. And then, diode should also survive the electroforming. Diode should be stable at various temperature. So even though people have resistive RAM, they have not been able to get this good diode. That is why most of the resistive RAM are in 1T, 1R structure, where transistor is used as an access device. Okay, so now what do you do if you have this device? Well, you can do a lot of interesting things. So this is your deep neural network. Everybody has drawn it, right? So you have this vector matrix multiplication, where you take this input, multiply it with the weight, but you have to think, well, where am I going to store this weight? So remember that first diagram I showed you, where you have to fetch the weight from the DRAM. So that is very intensive on memory bandwidth. So people say that, well, okay, so how about I integrate RAM in crossbar arrays and set it at different conductance state. Now think about it. For those of, that is where electrical engineers come into the picture. Kirchhoff's law, remember Ohm's law, Kirchhoff's law, that's all it is. So you have the voltage applied, and voltage intrinsically gets multiplied by the conductance of this device. So the current that you get through this device is a function of the conductance multiplied by the input voltage. And you can just sum it on this wire. And then at the end of it, you have to figure out the peripheral circuitry. Some people just have a sense amplifier that goes through it, and then it goes to analog to digital converter or something. I think Dr. Cody Merkel is better than me after figuring out what to do with this. But you have to design a peripheral circuitry. But using this resistor, you can, with multiple states, you can get intrinsic multiplication of input voltage with the conductance state. So that is the gist of where people want to make use of RAM. Now you can say, well, why RAM? Why not any resistor? Remember, you also have to program these devices to various weights. So that is why reprogrammable memory, that is what we need. Okay, so we made some of these devices. So on strontium titanate based switching oxide, so our stack was tungsten, strontium titanate as a switching, and then tinitride. We make this whole crossbar structure. One thing that we see is that our devices, these devices, show retention as a function of what kind of pulses come. So this chart is a little complicated to read, but you can see x-axis here is the type of spike you are doing, and this delay is between voltage applied to next voltage applied, how far they are. This axis here is the amplitude of the pulse, and this is measuring just the relative change in the conductance of the device. So if these two spikes come very close, you see a very big change in current if amplitude is also high. If these spikes are farther apart, then you don't see that much of change. So this is kind of unique type of device where conductance is a function of what kind of pulses are getting applied, programming pulses that are getting applied into these devices. So we made use of it to demonstrate some applications as a dynamic state memory. So again, we integrate these devices in crossbar arrays. For those of you who work with spiking neural network, I know Corey does a lot of work. And there is this whole algorithm called spike time independent plasticity, where pre-neuron and post-neuron, when they spike, based on that, you potentiate or depress these waves. So here, what we did is, in material of, if they are paired together, that is, if they spike together, we just potentiate it. But if their post-neuron are not paired with the spiking of the pre-neuron, then we let the memory decay. So memory is decaying. It's not a non-volatile memory in that sense. It has some decay. But by tailoring your learning algorithm, you can make use of this decaying states for the advantage of your neural network. That's what we tried to show here. So we call these memory devices as short-term memory devices. So we created this architecture, as I was saying, to get the attention of these architecture folks, we have to show the recipe. So this is the recipe with the ingredient. So we created this whole architecture. We have this short-term memory with STO, the strontium titanate devices, and we use it for training. And once we are satisfied with where it is, we threshold the weight and transfer it to long-term memory. Now, this long-term memory could be a two-state RAM, or it could be some register or SRAMs or DRAM, whatever you want. But at least for training, you can make use of the short-term memory, and it's actually pretty effective. So we showed it that with single layer perceptron, with spiking, making a deep neural network is very difficult, right? A lot of people have not been able to do it. So this was a single layer perceptron. With single layer perceptron, with this self-decaying memory, you can get 70% efficiency, which is comparable. But then we also have to figure out, well, what is the ratio of potentiation to self-decay of the device? And all these areas which are green, that is a good ratio for the rate of potentiation and rate of self-decay for these devices to give you the computing you're interested. So do you guys have any questions from the first part before we begin?
Which layer YSTO has that problem? How does transition from short-term to long-term?
Well, we think it is when you are stressing the device, defects are just getting formed, and those defects are trapping the charge, but the whole filament is not formed. But once enough charges are trapped, then the whole filament is getting formed, and that is when it transitions to long-term state. But yeah, we need to do a better job at understanding physics now. We need to do more like this is our starting point.
I have a question on this selector device. You mentioned the diode leakage selector. Can the integrated diode be the MEM structure?
Intrinsically, by tailoring the
by making a short diode or something.
yeah, you can, but you need bidirectional diode. The diode that can turn on with the positive set current as well as the reset. Reset voltage is usually negative. So you need a Zener diode type of thing. So yeah, but you can. That is where a lot of research is actually going for that. Yeah, to come up with a Schottky device that can be. Yeah. Great. So now we were stuck with this two-terminal device and 1T1R. So I told my student, hey, how about, and in 1T1R, as you resistor, you can see that your write current is a function of the resistance state of the device, which is not good, right? So we came up with this gated RAM, which is nothing but same the two-terminal RAM, but we added an extra gate. So idea is to change the conductance between top and bottom gate through this transition metal oxide by controlling the defects in the transition metal oxide using this gate. So this is similar to the ECRAM, but ECRAM, they dope this oxide with lithium ions and stuff like that, mobile ions. We don't dope this, we just capitalize on the intrinsic defects that is in the oxide to push them towards this interface or pull them away from it. So that is what was the gist of it. Now these devices are rotated 90 degrees because for the RAM, top to bottom interface distance should be less than like 10 nanometer. And you can't do it lithographically, at least in university. So we had to do it in this tilted fashion because we could separate top and bottom electrode using 10 nanometer of silicon nitride. So the conductance happens through top electrode through this purple oxide and then bottom electrode. And using gate, we can toggle the or modulate the interface between top and purple, bottom and purple. So that was the whole purpose. So we were able to see some hysteresis where we could control the conductance between top and bottom electrode using the gate. We could do cycle up to 150 cycles. And that's where we need to work on right now, where we want to increase the endurance after that device starts failing, which is not good. And also retention. If you keep reading through the top electrode over the time, you will see a retention falling down. So we need to figure out how to stabilize these devices, or we need to figure out how to make use of these decaying states for certain type of applications. But if we can do that, we can do a lot of interesting things. So this is a gated RAM model that we have made it available for the circuits community to do more simulations. And I think Cody was also involved in the advising the thesis of my student, Alex Jones, who is now at Riverside Research. So we have made this model available. You can take this model, integrate it in this configuration, and you can figure out how to make use of the gate terminal. So there is a great paper which talks about a 3-factor learning. And Cody and me in past have also talked about it. So instead of your weight update being just a function of pre and post, you can bring a 3rd factor which you can supply using gate to do the programming of these devices. And this paper talks about, how you can use neurotransmitter as one of the ways as a 3rd factor to do the potentiation and depression of the synapses. So those are all interesting things you can do with this new device technology. Now, finally, people start asking, well, if you have 3 terminals, it will be more, it will take more space and it is not scalable. But that is actually not true, because 2 terminal, you need a transistor, at least state of the art, 1T, 1R. In this case, you don't need a transistor. Like what Santosh was saying, in here, in these devices, if you look at it, you can, since you are controlling it through the gate, you can leave the bottom to this interface to be a Schottky while gate is pushing in and pushing out the vacancies. So you don't need a bidirectional diode. A Schottky diode can serve the purpose, and that is pretty achievable by engineering this bottom electrode and this interface over here. So that was the objective. So we did some architecture, some integration analysis, and we have shown that, well, scalability is pretty similar to 1T, 1R for these devices. And we did some analysis of gated RAM with the NeuroSim, which a lot of people use to benchmark new device technology. So instead of this 1T, 1R, we replaced, this is the FEFET version of it that other people have used, but we replaced the 1T, 1R with gated RAM and did some study there. And we saw that total area for default RAM and gated RAM is pretty comparable. Compared to SRAM Synapse, it's actually pretty promising. And other area of interest with the gated RAM is that with the gated RAM, you can see that write latency is a lot smaller than with the 2T RAM. That is because in 2T RAM, you need to have that transistor, and programming technique is limited in terms of parallelism. But for the 3T RAM, you can do a lot of parallel programming. You don't need to worry about the transistor. So apparently the write latency could be smaller. So these are some of the benefits, but we need to more study these devices in architecture and circuits to really establish these factors. And finally, the ferroelectric, which is very famous, right? I think Dr. Kaini is also working on it. So this device technology is very promising for a lot of application, particularly for neuromorphic application. The advantage of this is it's just a simple field effect transistor that we all know, but people can just modulate this gate stack using ferroelectric material, and you can tailor the VT of the device. So now you can get multi-state VT, you can get two-state VT. It's very, this ferroelectric oxide could be hafnium zirconium, which is very CMOS compatible. So there are a lot of benefits that people think this device can offer. So for those of you who don't know, so this is a simple NMOS. The gate stack, in this case, gate stack oxide is ferroelectric material. When it is polarized, so ferroelectric material, you can reconfigure the polarization, which in a nutshell is a distribution of charge in this oxide material. So when it is polarized in this fashion, these positive charges are here. And then if this is a P silicon working in inversion, you can get a low VT configuration for this device. If you polarize the dielectric in this fashion, then you can get a high VT configuration of this device. Now, all these domains, some of them could be polarized up, some of them could be polarized down. In that case, you can get intermediate VT states between low VT and high VT. So this device, if it works, it is very, very fascinating. And it has a theory that goes behind it. So people are very interested. So now going back to that DAXI Shochi program I talked about, I had this student who worked with Air Force Research Lab on barium titanate material. So they have this pulse laser deposition facility. They have this barium titanate, and they apparently this material shows very good ferroelectric behavior, and that was done there. So the stack we had, it's not CMOS, but you can still integrate it in thin film transistor type architecture. So it's niobium doped STO, PTO, and then simple capacitors. We did a lot of polarization characterization to show that indeed it is ferroelectric. And we see that it has remnant polarization, which is a function of programming voltage. So you can consider it as a multi-state VT device. So now, how do you, to make use of these things, you need to have a model, right? And getting model for ferroelectric field effect transistor is difficult. There are a lot of models out there. One of them is using this LK equation. You model this curve, and then you can go more elaborate on extracting the VT. We took a simple approach, right? So this is just, we treated it as an oxide charge. And then from there, we extracted the change in VT. And this oxide charge is just derived from the remnant polarization in the oxide. So now this is just an example of how you can get multi-VT, multi-state VT by polarizing different domains to different extents and stuff like that. So now what do you do with it? So yeah, jumping straight to brain is difficult, but I wanted to show you, a lot of people have used ferroelectric FET just for dot product and things like that. But there is this very nice neural network called self-organizing feature map. All it does is, this is an array of neurons and it gets some input. And what inputs do here is, this is the, what it does is it tries to find the best matching unit. Now, how do you find the best matching unit? So what it does is Euclidean distance calculation between input and this weight. So Euclidean distance calculation is nothing but input minus weight, and you square it and then you summate it. That's all it does. And the neuron for which the error is minimal, you call it a best matching unit. And then there are rest of the things that follows after it. But what I want you to is focus on this equation, which is calculation of the error, which is input multiplied by the weight, input minus weight squared, and then summation of that. And that is what we made use of ferroelectric FETs to do it. Now, for those of you who know the FET equation, MOSFET equation, long channel MOSFET equation, you know that the drain current in saturation for this MOSFET is proportional to V in and the threshold voltage of this device squared. So a MOSFET in long channel saturation, it intrinsically calculates the Euclidean distance between input, which is gate, and the threshold voltage. So we can make use, and since in ferroelectric FET, you can change the VT of the device, which would be weight, you can use these devices with reconfigurable VT to calculate this Euclidean distance. But then the drain current is very small if threshold voltage is higher than the input voltage, right? So for that, we need another FEFET where the VT of this FEFET is applied as the input and threshold voltage is programmed as VA. So there are some overheads associated, but using this paired FEFET approach, you can calculate the Euclidean distance between the input, and then you can tailor the threshold voltage to reach to the input to meet the criteria of this SOFM algorithm. So this is the whole architecture we have developed, input, and then each of these cells are FEFETs. You need to have programming circuitry for FEFET, which has these control signals, and then rest of the circuitry that we need to develop. But apparently using this array of FEFET, you can calculate the Euclidean distance, which serves as the basis of this self-organizing feature map. So what can we do with it? So taking that device model, the student showed that with 64-state FEFET, we can do very nice clustering of colors using this FEFET synapse. And these are pretty robust against various types of VT offset and variance, simply because neural network is an iterative process. So over the time, if you have VT variance and all, it does not have that detrimental impact as reading a memory device. So it shows very promising characteristic. And then some people also asked this question, well, these are analog devices, what about the variance? So again, if you model it as a Gaussian error on the current, all types of temperature variance and stuff like that, it is still pretty robust simply because of the iterative nature of the neural network algorithms. And then short channel FEFETs, this alpha is not exactly square. It has channel length modulation and stuff like that. So as long as alpha is greater than 1, we can still do pretty good clustering using paired FEFET. But if alpha becomes close to 1, then we start to see problems. So I think this FEFET, if we can think about relatively longer devices where we are using a lot of input data, where we are trying to reduce the data dimensionality or doing some clustering, these FEFET with this reprogrammable VT could be very promising. So that brings me to the conclusion. Conclusions are that you saw that RRAMs, gated RRAMs, FEFET, they have issues, but they still are pretty promising device for upcoming technologies for computing, such as AI and machine learning. We showed that gated RRAM is a viable option for overcoming some of the problems with 1T, 1R. In terms of scalability, it's pretty comparable to 1T, 1R. It can be integrated in CMOS backend, which is kind of interesting. And then we need to do additional work. I showed you that, well, we are in search of good switching offset. That's what we are looking for. So there are some work that needs to be done in that space. And finally, FEFET-based memory, not only can it do dot product and vector matrix multiplication, we can leverage this technology for Euclidean distance calculation, which serves as a basis of clustering. So that is the end of my talk. And I definitely want to thank Corey for giving me a chance to visit RIT, all students who have been doing research. And yeah, funding will be